Well, what we're going to do next here is we're going to try and come up with a way of quantifying what the energy is that's stored in the motion of an object. And the way we're going to do it is we're going to pose this situation that's described here. We have an object that starts out at rest. It drops through some distance from height 1 to height 2. And here, obviously, it has no velocity. And down here, it's going to have some final velocity that's non-zero. The question is, how much energy is stored in the object's motion? Well, thinking about what's happening here with this object, when it starts out up here, it has a velocity of 0, and it's got some potential energy. The amount of energy that's stored in its position is mgh1, because it's at height 1. And then it's going to drop down to some lower position here, and the potential energy that it has here is mgh2, which would be less, obviously, because h is a smaller number at h2 than h1. Well, the law of conservation of energy says this. It says that the sum of the kinetic energy at state number 1 and the potential energy at state number 1 must be equal to that same sum at state number 2. Well, we already have established that there's no kinetic energy at state number 1 because it's at rest. So we could rewrite this equation and we could say the potential energy at state 1, which is just mgh1, is equal to whatever the kinetic energy is at state 2, there's no sum because there's only one object, plus the potential energy at state 2, which is mgh2. And what we're trying to do is find out Ke, too. We're trying to figure out how much energy is stored in the motion of this object. So let's just isolate that by taking mgh1 and subtracting mgh2. We'll do that to the other side of the equation as well, which will just leave us with Ke2. So that's the energy that's stored in the motion of the object at position number 2. By removing the mg from this equation, we get mgh1 minus h2 is equal to Ke2. Well, I want to somehow relate this to how fast it's going. If energy is stored in the motion of an object, it'd be nice to be able to relate it to something that measures its motion, like velocity. And here's what I know. During this fall, it's being accelerated. So its final velocity is equal to the square root of its initial velocity squared plus 2 times the acceleration that's under times the distance. But it started out with no initial velocity, and the acceleration is the acceleration due to gravity. So we could say that the final velocity is equal to the square root of 2 times g times the distance that it fell. Now, the distance that it fell is related to h1 and h2. So we could say Vf is equal to the square root of 2 times g times h1 minus h2. If we square both sides, we get Vf squared is equal to 2 times g times h1 minus h2. Well, this h1 minus h2 term, that appeared in the other equation that I had. mg times h1 minus h2 is Ke2. So I'm going to solve for that. First, I'll clean this equation up a little bit. Vf is equal to 2g times h1 minus h2. So if I divide both sides by 2g, I find that h1 minus h2 could be replaced with Vf squared over 2g. That Vf was squared there. So substituting that for h1 minus h2 in my equation that quantified Ke, the kinetic energy at state 2 for this moving object is equal to mg times h1 minus h2, it said. Well, that's then equal to mg times Vf squared divided by 2 times g. And the g's cancel out of here, and this leaves me with this equation. M times Vf squared divided by 2. That's how much kinetic energy the object has. So we can extrapolate this to any general situation, and we can say that the energy that's stored in the motion of any object that has velocity v is equal to 1/2 of that velocity squared times the mass of the object. So this would be a very valuable equation to possibly pop in your toolbox. Kinetic energy is 1/2 the mass of the object times its velocity squared. Well, here's an example that will allow us to apply that. We have a baseball. Its mass is given. It's 145 grams. That would be 0.145 kilograms. It's moving at 90 miles an hour. Probably want to change that. How much energy is stored in the baseball's motion? Well, we know that the answer to this is going to be 1/2 the mass of the baseball times its velocity squared. So let's get the velocity of the baseball in meters per second so that we can come up with joules. So 90 miles per hour is our starting point. We want to get this into meters per second. An hour is 3,600 seconds. So that gives us seconds. A mile is 5,280 feet, and that would get us into feet. And then a foot is 12 inches, but an inch is 2.54 centimeters. So now we're in the SI system, and 100 centimeters is the same as a meter. So that gives us meters per second. And the speed is 40.2 meters per second. So now we'll put that in here for V, and we'll quantify kinetic energy. So KE here is 1/2 the mass of the baseball, which is 0.145 kilograms, we decided, times the velocity of 40.2 meters per second squared. Square meters per second, and you get meters squared per second squared. Multiply that by kilograms, and you've got joules. Our answer numerically is 117 Newton meters, or 117 joules. Well, there's another analogy, a rotational motion analogy here. We know that for linear motion, KE is 1/2 mv squared. In a rotational system, KE would have to be equal to the 1/2 times the analog for mass. The analog for mass is in the moment of inertia I, times v squared, but the analog for v is omega. So we're going to square omega. Here's an example problem that allows us to work with the rotational version of kinetic energy. It says a flywheel is shaped like a disc and has a mass of 100 kilograms. Diameter is 61 centimeters. The wheel is spinning at 540 RPMs, and the question is, how much energy is stored in the motion of the flywheel? Well, not everybody knows what a flywheel is, so I should probably spend a little time talking about that. A flywheel is a device whose only purpose is to store energy in motion. Usually it's a heavy disc made of metal or sometimes concrete or something, and it spins around, and its spinning motion of this mass stores energy. And the amount of energy that's stored, we realize, is obviously 1/2 I omega squared by the equation that we just developed. So obviously we're going to have to find out what I is. If this is a disk, it's going to be 1/2 mr squared. So plugging in information that we know here, the mass of this thing is 100 kilograms, it said, and its diameter is 61 centimeters, which would be 0.61 meters, and then half of that would be the radius. So we would end up with 0.305 meters, and that's going to be squared. So our moment of inertia for this flywheel is 4.65 kilogram meters squared. Well, we also want to find omega here for this equation. We know what omega is, actually. It's 540 RPMs, or 540 revolutions per minute. But to get our units to come out to joules, we want to change this into radians per second. Here's how we can do that. We know that a revolution is 2 pi radians, and we know that a minute will be 60 seconds. And so this will give us radians per second. When you do this calculation, you get 56.5 radians per second. So the kinetic energy stored in this flywheel is 1/2 of I, which is 4.65 kilogram meters squared, times 56.5 per second, and that's going to be squared. The units that we get will be kilogram meters squared per second squared, and that's joules, or Newton meters. And the numerical answer is 7430.